Hello everyone, my name is Suciu, and I'll present a set of new horizontal privilege escalation attacks that we have found in TrustZone-based systems. First, let me begin with a little background. We all know that over time, the cost of applications and operating systems have increased dramatically. As a consequence of code increase, the number of vulnerabilities present in applications and OSes also have increased. TrustZone represents one of the solutions to mitigate the impact of a compromised OS. Under TrustZone, most software runs in a normal world under a rich operating system like Android. In addition to a normal world, the processor can also execute security-critical applications, also known as trusted applications or TAs, inside the secure world. These TAs run isolated from normal world alongside a secure OS. In TrustZone, the normal world applications can not only directly communicate with the rich OS, but also with TAs through shared memory with the help of the two OSes alongside a monitor. The key of the TrustZone architecture represents the fact that secure OS software and our devices are protected from direct access of a compromised normal world. Moving applications inside the secure world, however, does not completely protect them against attacks from the normal world. Privilege escalation vulnerabilities exist in both the normal world and secure world. For example, if the rich OS is vulnerable, a compromised normal world app can escalate its privileges into the OS kernel. Once inside the kernel, the attacker can target vulnerabilities inside TAs. TAs, in turn, can be used to target secure world vulnerabilities. Once the secure OS or monitor is compromised, attackers have complete control over the device. It is also important to note that TrustZone can also introduce new attack vectors into normal world software. For example, vulnerabilities inside the secure world can enable applications to exploit their communication with TAs to launch Boomerang attacks. Briefly, in a Boomerang attack, an application tricks the TA into modifying normal world data or code, including the rich operating system. In all the attacks described, the attacker aims for vertical privilege escalation. In other words, he aims to obtain more control by compromising higher privilege code. In contrast, in horizontal privilege escalation, or HPE in short, the attacker aims to obtain access to data or code in software running at the same privilege level. For example, using a regular app to compromise data belonging to another regular app represents horizontal privilege escalation. The main focus of this presentation represents attacks that enable horizontal privilege escalation. Now, I will focus on showing how malicious normal world apps can compromise or leak data belonging to other normal world apps by leveraging TAs. These attacks require no vulnerabilities inside higher privilege software. Instead, they target the multi-tenancy and statefulness of TAs. First, let me explain how TAs manage data received from normal world apps. Each TA typically represents a secure world service that receives requests from one or more normal world apps. Similar to web services, they can maintain application data across multiple invocations. They can keep it in their global memory or save it on persistent secure world storage. However, there exists a semantic gap between the normal world and secure world that prevents TAs from knowing the identity of their client apps. Problems arise when TAs manage data of apps without knowing their exact identity. For example, a TA can expose a victim's app's data to malicious applications. Once a victim writes data into the global memory, the malicious app might be able to read it. Or, once it is written, it can try to modify it before the victim reads it back. If the data written is a decryption key, a malicious app could also try to trick the TA into using it to decrypt content for it. Similar attacks can be performed when TAs store data in secure storage. The key difference is that any TA with access to the respective storage could be leveraged by the malicious app in order to leak or compromise data within. More details regarding these attacks are presented in the paper. We've analyzed a total of 95 TA binaries for vulnerabilities that could enable horizontal privilege escalation. These binaries have been extracted from 3 different TrustZone-based trusted execution environments: Kinibi, Qualcomm Secure Execution Environment or QCE, and Teegris. These TAs are written by multiple parties and not by trusted execution environment vendors themselves. Inside the TA binaries, we identified 3 types of horizontal privilege escalation vulnerabilities. For each TrustZone environment, we have grouped the TAs by the main functionality. For example, TAs managing DRM data are denoted as DRM. Those performing attestation are under attestation, and so on. Each column shows the number of vulnerable TAs identified in each group. Let's take TAs running under Teegris as an example. 1 out of 2 DRM TAs contain vulnerabilities that allowed leaking or compromising sensitive data. 25 key management TAs expose cryptographic keys, and all 3 attestation TAs contain at least 1 horizontal privilege escalation vulnerability. The TAs in the other groups were mostly stateless or did not manage significant non-model data across invocations. It took 2 engineers 4 weeks to analyze the 95 TAs running under the 3 OSes. For each vulnerability, we have determined its impact and how it can be used by a malicious application. As a result, we have identified a total of 5 horizontal privilege escalation attack vectors. TAs can be used to leak data, compromise data, or act as decryption, encryption, or signing oracles. For example, a TA leaking an encryption key has a data leakage horizontal privilege escalation attack vector. More details are provided in the paper. Here's a glimpse of the attack vectors discovered in TAs running under each TrustZone environment. I will not go into details right now, but if we take TAs running under Teegris as an example, 6 vulnerabilities lead to key leakage, 5 to data compromise, 4 are decryption oracles, 2 encryption oracles, and 7 signing oracles. Out of this, 9 were in attestation TAs, 6 in key management, and 9 in DRM TAs. In order to speed up the analysis process for horizontal privilege escalation detection, we have designed and implemented an automatic HPE detection tool. We have named the horizontal privilege escalation detection tool HOOPER. HOOPER consists of 3 phases. First, HOOPER takes a TA binary and uses symbolic execution to analyze its execution paths. The resulting path semantics are then collected and used in phase 2. Here, the execution paths that restore data are paired with those that have written it. In phase 3, the paired execution paths are examined in order to determine if normal application data written in one execution path can be leaked or compromised using another execution path. All such execution paths are reported by HOOPER as containing potential horizontal privilege escalation vulnerabilities. To give you an intuition on how application data is tracked across multiple execution paths, let's consider the following example. A TA contains a bunch of execution paths. One is writing input data to a global variable X. Another writes X to an output. And another pair of execution paths share data using a storage Y. If a victim TA uses one execution path to write data into X or Y, an attacker would read it by using the left and right paired execution paths. HOOPER finds and reports the cross-invocation data flows between these paired execution paths by using the described framework. We run HOOPER on the TAs running under Teegris. Briefly, 15 out of 20 attack vectors have been identified automatically by HOOPER. The other 5 were missed due to symbolic state explosions or incomplete emulation of Teegris provided functionality. It is important to note, however, that HOOPER identified these vulnerabilities within 24 hours, in contrast to the 4 weeks spent on manual analysis. Automatic analysis is helpful in identifying vulnerabilities already present inside TAs. However, it is preferable to prevent these vulnerabilities from being introduced at all. In the paper, we describe a set of potential mitigations against the discovered attack vectors. Briefly, standardizing session management, resolving multi-tenant interference, and minimizing access to TAs and secure resources could help prevent the appearance of horizontal privilege escalation vulnerabilities. In conclusion, some TA store data from multiple applications, either in global memory or secure physical storage. These vulnerabilities appear due to insufficient access control that exposes the data stored by TAs to attackers. We have identified 3 types of horizontal privilege escalation vulnerabilities in 23 out of the 95 analyzed TAs. Automatic binary analysis can help find these vulnerabilities significantly faster and with a fraction of the effort. Finally, platform-wide fine-grained access control could help avoid introducing these horizontal privilege vulnerabilities in the first place. Thank you. Feel free to contact us and ask questions.